In this video, what we're going to do is we're going to learn a little bit about mathematical proofs. I find it actually kind of ironic that here I am saying watch the video in the middle of the video, so you're obviously watching. So a proof, what is a proof? A proof is a way to demonstrate the truth of some sort of mathematical statement. Okay, we're going to start off with particular types of proofs where we have a conditional statement, if A then B. In order to do that, we're going to start off with some rather common ideas, even and odd integers. In order to do that, we need to know exactly what we mean by an even and odd integer and then use that definition consistently. We're going to say an integer n is even if there's some number k in the integers for which n is equal to 2 times k. I've got a couple of examples below. On the other hand, we're going to agree that when we say an integer is odd, that means that n is 2 times k plus 1 for some integer k. You have a common sense as to what even and odd integers are. You probably look at the last digit of your number. But if we use the definition, 254 is even. Why? Because we can find some integer, 127, that when multiplied by 2 gives us 254. 991 is odd, not because it ends in a 1, but because there's some number, which happens to be 495, an integer, that when multiplied by 2 and then add 1, we'll get 991. And finally, another example, negative 17 is odd because there's some number that when we multiply it by 2 and add 1, we get negative 17. In fact, 2 times negative 9 is negative 18 plus 1 is negative 17. Now, we are going to insist when we talk about odd integers, it has to be plus 1 at the end. You might have said, wait, I've got this. Negative 17 is 2 times negative 8, which is negative 16, minus 1. Negative 8 is an integer, and so that's how we know negative 17 is odd. We're not wrong that negative 17 is odd, but we are wrong in the way we've applied the definition. The definition of odd always requires that we add 1 after multiplying by 2. Notice that the definitions have a name over here and then some sort of mathematical expression. So we can go back and forth between the two of them. That's what if and only if means. If one is true, then the other must be true. So I'm going to ask you to do is go through the worksheet here and fill in the blanks in this first exercise as we go. So I want to read through the proof. I want to make some comments, and then in the blanks, I want you to fill in those what I'm saying. So we're going to start off by supposing or proving that the square of any odd integer is odd. Not just 3. 3 squared is 9. 3 is odd. 9 is odd. Woohoo! 11 is an odd number. If we square it, we get another odd number, 121. Woohoo! We want to prove it for every single case. And it's best really to say this in another way. Given any odd integer. Okay, well, let's start with any integer whatsoever. And then we're going to check to see if it's odd. If it is odd, we want to show that n squared must be odd. Okay, so that's how we'll start this. Let n be any odd integer. So we're saying if n is odd. Okay, now, why are we adamant about saying any? I've already covered this, but the reason we're adamant about saying any is that we want our proof to work for every possible odd integer. So in that blank, put want the proof to work for all odds. Now, what we could do in the end, and we're not going to do this, but what we could do is we're going to introduce some variables. When we introduce these variables for very specific odd integers, let's say 1991, we could choose the values of k that we need and show that it works for that particular one. Okay, so now let's back up where we were. Let n be any odd integer. Now, what are we trying to prove? We're trying to prove that n squared is odd. So it's helpful to say what we have to prove. We must prove that n squared is odd. Let n be any odd integer. We must prove that n squared is odd. The reason this is particularly helpful to do is when we get stuck. So in this little second box, when we're stuck, that's why we're often going to say, what is it that we have to prove? Now I'm going to state, okay, what does it mean for n squared to be odd, right? We have to prove that n squared is odd. Well, that means n squared must be 2 times some integer plus 1. Now our definition says 2 times k plus 1, but we can say 2 times any integer we want. And so I want to find an integer j so that n squared is 2 times j plus 1. Okay. Since n itself is odd, there is another integer k. Now notice I've already used the letter j, so I don't want to use j again. There's an integer k for which n is equal to 2 times k plus 1. Okay, now here's the magical moment. We have this new expression for n, and so what we can do is we can substitute that expression into n squared. So here we have n squared, n was 2k plus 1, n squared is going to be 2k plus 1 quantity squared. Okay, and now in this next step, all we're going to do is a little bit of algebra. If you FOIL out 2k plus 1 times 2k plus 1, you get 4k squared plus 4k plus 1. Now our goal is to write this as 2 times some integer plus 1, right? We want n squared to be 2 times some integer plus 1. And we've just done it. 2 times 2k squared plus 2k plus 1. N squared is 2 times some integer plus 1. Now, we probably want to make some assumptions. In here, we started off with k being an integer. Well, if k is an integer, then 2 times k would also be an integer. K squared would be an integer, because when you multiply an integer by another integer, you get an integer. That's the same reason that 2k squared would be an integer, and overall this value is going to be an integer. So there are some rules about integers that we're going to assume to be true. All right, so now we have n squared is 2 times some integer plus 1. I can be very explicit and say, hey, let's let that orange or the yellow stuff there, let's let all this stuff be equal to j. Then n squared is 2 times j plus 1. Okay, since n squared is 2 times j plus 1, we've shown that n squared is odd. That's the general idea with one of these proofs. We're going to look at another one. Now, notice over here in this area, it's nice and pretty. Everything is lined up. Do you see that? That is basically drawing the reader in and saying, hey, watch, I'm about to perform really the crux of the argument. Okay, and that's what's known as displayed notation. So over here in this little box, what is it called when we center the main work? It's called displayed format. So you can put that in there. In the next proof, we're going to kind of tidy things up a little bit. We're going to make a little bit shorter proof. We really do not need to do this part of things, right? Here we said we have to prove that n squared is odd. And then we thought, what does it mean to show something is odd? It means it's 2 times something plus 1. We don't need to do that. In fact, we actually don't need to state that we must prove what we must prove, but it's often very helpful. And we'll talk about that in just a little bit. Okay, so the part of the above proof that's overkill is when we made the substitution for j to be equal to 2k squared plus 2k plus 1. In fact, the whole line that I'm about to highlight here is probably overkill. So this line here where I'm highlighting in blue, in other words, we must find an integer j, that's overkill. We don't really need to introduce an extra variable. Okay, so let's look at another proof here. All right, so what I want you to do here is I want you to write the proof of this result as we go over it, or maybe watch the video and then go back and try to recreate the proof on your own to get some practice. If you have any questions as you do this, I would love for you to write them down in this space. Okay. Suppose m and n are any integers, all right? So they can be anything we want, and then we're going to narrow them down. If m is even and n is odd, we're going to prove that 5m plus 9n is odd. Okay, now we're not going to use results that we know, like an odd integer times an odd is an odd. We're not going to use that. We're going to go back to the very definition of even and odd. Okay, so here we go. So what I'll do is I'll start off by saying, we'll say let m and n be any integers. Okay, and now we're going to narrow it down. And we're going to suppose that m is even and n is odd. Okay, so what I must show, and I'm not going to write this down, you don't always need to, but we're going to talk about that on the next page. We have to show that 5m plus 9n is odd. I'm not sure I have enough room, so I'm not going to write that particular step in here. So we'll come back to that in a moment, but I'm going to use the definition of even and odd in order to write m and n in different forms. Then, well, because m is even, m should be 2 times k for some integer k, and since n is odd numbers are one more than a multiple of 2. So n is 2 times j plus 1. Now, we haven't specified what m and n are, or j and k are, for some integers j and k. Now, you notice that I chose j for one of our variables, n, and k for the other. The reason we do that is because if I chose them to be the same thing, then that would mean that m was just one less than the number n. Remember again what we have to prove. We want to prove that 5m plus 9n is odd. So we're going to try to write that as 2 times something plus 1. So let's look at the quantity 5m plus 9n. And we'll often say something like, consider or then 5m plus 9n is equal to, now we make some substitutions here. This will be 5 times m, we said was 2 times k, plus 9 times n, we said was 2j plus 1. Okay, so we've made our substitutions. We're looking at the quantity we're trying to prove is odd, and now it's a matter of algebra. So we want to multiply the 5 times the 2k, we're going to get 10k. We're going to distribute that 9 through. That'll give us 18j plus 9 as our answer. Now, again, we want to write this as 2 times something plus 1. We don't have a plus 1. In fact, we have a plus 9. But what you want to remember is that every odd integer can be written as something plus 1, right? 9 is 8 plus 1. So in the next step, we'll say this is 10k plus 18j. Let's make this plus 8 plus 1. And now notice that what we have here is everything has an even factor. So what we can do is we can factor a 2 from that. So this is equal to 2 times 5k plus 9j plus 4 plus 1. And now we're going to write a little bit of an abbreviated version of what we did before. What did we just do? We showed that 5m plus 9n was 2 times some integer plus 1. So we're going to write a little concluding sentence. We showed it was odd. Okay, so here we go. We'll say, thus, 5m plus 9n is odd. Why? Since, well, let's see, 5m plus 9n we showed was equal to 2 times 5k plus 9j plus 4 plus 1. And that stuff that we had inside the parentheses there, 5k plus 9j plus 4, that's going to be an integer. And (5k plus 9j plus 4 is an integer. That is, 5m plus 9n is 2 times some integer plus 1. There's our proof. So the rest of this worksheet here that you're going to do, I've started some proofs here. None of these proofs are you're going to finish. Don't worry about finishing any of these proofs. But I give you sort of the beginnings of them, and you're going to have to finish them. So, here's an example. Here's the result you would be trying to prove. You might not even know what these terms mean, but that's okay. Given any real valued function, notice this is a universally quantified statement. Given any real valued function f, if f is differentiable, then it is continuous. That is, then f is continuous. So what do? We say suppose f is any real valued function, given any real valued function, to prove it's true for every single one. Then you're going to take your hypothesis of your conditional statement, suppose f is differentiable, and you're going to state what you must prove. We must prove that the conclusion that f is continuous. I'll give another example, and then I'm going to ask you to go through and give what the proof starts should be. Don't go beyond what we did before. And then as your final thing, you're going to write a couple of proofs for me. You're going to see that they're related, and then you'll discuss some things about converses and contrapositives and all those lovely things.